Hello, everybody. I hope you hear me. And somebody,
Oi.
you hear me. Excellent.
Yeah,
Thank you.
Yeah, you're there.
So, welcome to this next session, which is session number 5 on sound synthesis. I'm Vesa Välimäki, and I'm a chair of this session. So we will have 3 papers, and we will hear the video presentation for them without breaks. And during this time, you can click the Q&A button and write your questions or comments to the speakers. Please remember to mention who you are writing to, because otherwise, in the end, we will not know who. We can try, but you might not know who should answer the question. So the 3 papers are, the first one is recreating the Amoeba Violin using physical modeling and augmented reality. The second one is Datatonism, emulating historical instruments as a pedagogic exercise. And finally, the third paper, a Faust-built mobile vocoder instrument. So now let's enjoy these 3 presentations and then we'll get back.
Hi, and welcome to our presentation about the digital recreation of the Amoeba Violin, also known as the Violino ARPA, using physical modeling and augmented reality. This audio-shaped instrument originates in the 19th century Vienna. The muddy sound it produces was not favored by the musicians of the time, and only a few pieces were eventually created. One of them is now in display at the Danish Music Museum in Copenhagen, but as with most historical instruments, it is not available to play. For this project, we recreated it digitally to inform about the history of the instrument and its sonorities. The project was created in response to the COVID-19 outbreak, the official calls to stay indoors, and the necessity for reduced use of shared surfaces that followed it. It is noteworthy how the entire experience of visiting a museum has changed in the recent years. What used to be a passive experience has now become much more interactive with the implementation of various tools. Digital media, and particularly AR and VR applications, are key players in that shift, as they have been shown to help make the visitor experience more engaging and memorable. In fact, the earliest example of a full AR implementation in a cultural heritage site was in 2001, at the sites of Pompeii in Italy and Olympia in Greece. The system used there was able to produce quality results, aiding greatly in the further development of the technologies in the following years. The interactive application we created intends to provide a brief but concise set of information through gaming and exploration. The Amoeba Violin was selected because it is one of the most famous pieces of the Danish Music Museum. The application, however, works as a prototype that could be applied to more instruments in the future.
The application was built using Unity 3D. Multiple toolkits were also implemented, primarily EasyAR and DisplayMaker. Autodesk Maya was used to create the 3D components of the Violino ARPA, and Adobe Illustrator and Photoshop for the design of the instrument history. All of the sounds that are added in the application are simulations of what the instrument sounds like, designed in MATLAB, and implemented in real time using C++ and the JUICE framework.
The sounds of the Violino ARPA were produced using physical modeling sound synthesis. This implies using numerical simulation methods to approximate the instrument's vibration. This can be done with different degrees of complexity and consequent accuracy. This comes from the choice of how detailed we want to model the instrument's components. For example, how many degrees of freedom we want to consider for the vibration of the string, but also comes from the choice of numerical simulation methods. For example, finite element methods are more flexible and allow for the change in density across the plate of a violin, but are more computationally demanding. For this project, we wanted to allow for the possibility of a real-time implementation of the physical model as an upgrade, which was in fact extended as such in my master thesis. The Violino ARPA was modeled as a bowed stiff string rigidly connected to a resonant plate, and the partial differential equations for these different components are given in these equations. The first is for the stiff string, the second is for the plate, and the third specifies the rigid connection condition between the two. The various parameters are described in the table to the right. with the subscript S denoting the string and the subscript P denoting the plate. Also, the subscripts T and X denote derivatives with respect to time or space in x direction. I'm not going to go through all the parameters, but details can be found in the paper. Regarding the bowing excitation, we used an elastoplastic friction model, which had previously been applied to stiff strings by Willemsen and others in 2019. The system was simulated using finite difference time domain methods, which implies discretizing the space and time with some constant intervals. Then the derivatives in the partial differential equations can be approximated as some difference functions, and the state variable from which the state variable of the future time step can be calculated from values of the state variables at previous time steps. Hence, a solution can be propagated in time. Details regarding the solution can again be found in my master thesis. Simulations of bowed strings tuned to various musical notes were carried out and recorded in MATLAB, and then these recordings were played as sound samples in the Explorer app. Here I'm just going to give some examples of the sounds. So. So that's it for the sound part. Thank you.
The app consists of 4 scenes that are similar in both versions. In the first one, the puzzle level, the user faces a violino arpa, broken down to smaller pieces and has to connect them in order to create a complete instrument. With its correct movement, the harmonic sound of the violino arpa can be heard, and the pieces snap together. When the users try to stick the piece to the wrong place, an unpleasant sound is heard instead. In the second scene, the users have the chance to explore the instrument in further detail. The violino arpa is now presented in a single piece with the option to rotate it in 360 degrees. The third scene consists of a 2D story made of 20th century engravings. There, the users can scroll and see color integrated to the black and white engravings while reading some key information about the history of the violino arpa. Finally, in the last scene, the users come across a music player where each circle represents a note of the instrument. They can test different notes and decide for themselves whether they like the sound of it or not. A total of 23 subjects, from 12 to 39 years old, took part in the research experiment. All participants live in Copenhagen, where the Danish Music Museum is located. The goal of this evaluation was to test how AR technologies and non-immersive desktop applications can enhance the overall experience, cultural appreciation, and educational reinforcement of a virtual museum visit, and to illustrate the differences in effectiveness and popularity between these two. This was achieved by exploring the quality of both applications in terms of content, user interactions, and experience. In order to have highly accurate and valid results, qualitative data were gathered as the subjects were encouraged to think aloud and have been recorded while using the applications. Quantitative data collected from the subject after performing trials on both applications through questionnaires.
As an overall review of the data, most participants seemed to enjoy both experiences. Over 70% of them felt that both applications were interesting, easy to use, and would like them in the context of a museum. Around 65% of them seemed to be eager to explore the Danish Music Museum after using the applications. The same amount of participants also stated that this experience had an educational benefit, however most of them mentioned that the application was lacking in embodiment and continuity of narration. In the last part of the questionnaire, the participants were asked to state their preference between the two different versions of the application. The augmented reality one seemed to be preferred over the desktop one. However, no difference was recorded in terms of narration, educational content, and accessibility between the two versions. The experience of both applications was positive overall. However, many participants stated that they could use more gameplay instructions and expressed a strong will to mention the names of the notes so they can play short melodies. Additionally, they pointed out that it would be better if the buttons were activated with touch or hovering of the mouse. The limited number of test subjects affects the accuracy of the results. This was tried to be counterbalanced through the qualitative data that we gathered. The preference towards the augmented reality version was markedly higher, with participants pointing out that the ability to move around and see the poster is very important. What surprised us the most was that several of the subjects mentioned that the mobile application is more accessible than the desktop one. We were expecting the opposite, and we guessed the participants were biased because the testing of both applications took place in the museum. The excitement of using the augmented reality application in situ is likely to have obscured the added accessibility benefits of the desktop version, which can be used online. Both versions of the application were generally well perceived, and our findings indicate that a noteworthy percentage of museum visitors is likely to use such applications. We believe there is a great potential in using physical modeling and interactive technologies in order to facilitate a big social change in the museum experience, and therefore invite the scientific community of NordicSMC to delve further towards in this direction. Thank you very much.
Hi, my name is Derek Holzer. I'm a PhD researcher at the KTH Royal Institute of Technology in Stockholm. Today, myself and MA student Carolina Shi will be presenting Datatonism, emulating historical instruments as a pedagogical exercise. Datatonism is part of a larger research project about historically informed sound synthesis, which investigates instruments used by electronic composers in Sweden during the 1960s and 70s. These instruments are archived by the Swedish Performing Arts Agency and the Swedish Museum of Performing Arts. Partners in this project are also KMH, the Royal College of Music in Stockholm, and KTH. The goals of the Historically Informed Sound Synthesis project are to make digital emulations of the analog instruments from the collections, to make tangible interfaces inspired by the original artifacts, and to engage in collaborative design projects with composers, students, museum visitors, and an online audience around the further development of these instruments. There's a number of reasons why you would want to engage in the emulation of historical electronic sound instruments. It allows the playing of inaccessible and rare instruments. It allows the performance of compositions which depend on obsolete hardware and software for their realization. It allows one to explore and modify historical designs with the eye of making new instruments based on them. And finally, and most relevant to this context, it can be used as a platform to explore the study of digital musical instruments. The instrument emulated in this project was the Datatone System 3000. It was designed by Björn Sandlund in the 1970s and manufactured by his Datatone company between 1973 and 1980. It was a modular sound synthesis and processing system which was intended to be used in every Swedish music school, although that particular part of the project never got off the ground. We've done extensive work with the Datatone already in another paper which analyzed its affordances and its ethics for the NIME conference of 2021. The Datatone System 3000 contains several different types of modules to be emulated. There are source modules, which include oscillators and other signal sources, such as noise, manipulating modules, such as filters and modulators, editing modules, which largely are mixers and spatializers, control modules, which contain digitally stored sequences, which were not emulated during this project, and the power modules, which provide system power for the entire instrument. So here is the second tutorial. This has to do with the functions of the quad sound generator, which, as I mentioned, is 4 independent channels of oscillators. And there's a few tricks we can do with this. So this is about the simplest patch that you can make with the Datatone. You've got the power supply, which is feeding power to the modules through the A and the B bus. And then below the quad sound generator, we've got the universal mixer that's taking the 4 channels. Remember, you've got the A and B buses and you've got the 4 channels. So the 4 channels are coming down now to the mixer. And with this knob up here on the top, I've assigned them a stereo panning location.
Hi,
My name is Carolina and I'm the co-author of this paper. I am currently a master's student and studying interactive media technology at KDH. 7 students partook in this project as a team through the course Musical Communication and Music Technology at KDH. The students referred to the following research questions. What are the limitations of creating a digital emulation of an analog system? What compromises and design choices are required for the emulation? And how does one evaluate such an emulation? Throughout the emulation process, students were supported with PD crash courses held in Zoom. They also had access to a part of the physical system, as well as documentation containing descriptions of each module's feature, photographs of their interface and interior, and schematics of their circuits. The modules are connected by graphical patch cables to recreate many of the capabilities of the original Datatone. The Automatonism Library was used as a framework, which provided features such as multiple instances of modules, state saving, randomization, and interpolation between states of all module parameters. The modules themselves were hand-coded by the students. An online survey was created to evaluate the system. Users were asked to download and freely explore the Datatone System, and then answer questions concerning general familiarity with modular synthesizers and languages like PD and Max MSP, followed by questions about their experience using Datatonism. At the end of the course, students submitted one group report supplemented by individual feedback reports. The report concluded that compromises had to be made, especially in regards to keeping the look of the original system while having limited screen estate. Limitations of the digital emulation were also noted both by the students and users, such as missing tactile feedback from turning the knobs, and that digital sounds are fundamentally different from analog ones. The individual feedback reports were very varied. In general, the students thought the provided documentation to be essential, and some found the physical modules useful for comparison or clarification of features. The project having a solid framework was also appreciated. One student found it difficult to find appropriate resources beyond the provided material, while another discovered a wealth of sources for their particular module. Most reported an enjoyable learning experience with various benefits being mentioned. Some appreciated the opportunity to learn more about synthesis and design, while others benefited from the chance to practice teamwork, organizational, and leadership skills.
A larger discussion of this project focuses on the educational aspects of this process of instrument emulation. We found that it gave the students valuable lessons in the application of concepts from human-computer interface studies, as well as in the study of new instruments for musical expression, NIMEs. We also found that the students discovered that there's very important distinctions in terms of affordances between hardware and software-based instruments. And finally, we found that the modular project structure provided by Pure Data, and in particular by the Automatonism Library for Pure Data, mirrors the pedagogic intentions of the original Datatone by providing a very atomized and structured framework for the exploration of the instrument. In conclusion, we found that this process of emulating the Datatone 3000 as a pedagogic exercise provided rich benefits to the students' learning experience through the exercise of technical skills, teamwork, and creative thinking towards the realization of a new instrument based on a historical one. We thank you for your kind attention.
Hi everyone, I'm Riccardo Russo, a PhD student at the University of Bologna. Today I will present the paper Faust-built mobile vocoder instrument. This is the result of a project I did during the Master in Sound and Music Computing at the Aalborg University Copenhagen under the supervision of Professor Daniel Overholt. The goal of the project was to develop a mobile version of a vocoder in order to test the opportunities provided by smartphones in creating a portable version of this musical effect. So many works have investigated smartphones as platforms for the development of musical interfaces ever since their birth. From these, it's possible to outline some general advantages and disadvantages of using smartphones as portable instruments. First, smartphones nowadays have a high computational power, which allows to run more and more complex DSP algorithms. They have many built-in sensors. And an important feature is that when we develop an instrument in the form of a smartphone app, we know that the hardware, or most of it, will be already available, so there will be no need to build it. Also, this provides a wide user base, since most of the people nowadays carry a smartphone in their pocket. On the other hand, smartphones rely on touchscreen as the main source of input, and there are no knobs and limited keys. Touchscreen also doesn't provide any tactile feedback, which is very important in musical instruments. The hardware is not designed for music, meaning that, for example, data coming from sensors needs to undergo some pre-processing before being used for musical purposes. There are limited audio connections. So usually smartphones have a speaker for reproducing audio, and there are only jack connections sometimes, and Bluetooth connections for interfacing with other audio devices. There are also some operating systems limitations. Among many studies, Geiger studied the usage of the touchscreen itself as a controller. First, he mentions that the touchscreen allows to overcome the classic Windows icon menu pointer interface, which is notoriously difficult to handle in live musical performance. Then he defines a list of principles for the development of instrument interfaces with the touchscreen devices. So the interface should be one piece, be easily portable and usable in different social contexts, have an interface which maximizes control and gives immediate feedback, and be learnable and masterable. The instrument, the vocoder, was built to be compliant with these principles. Some details on the application. It was built with the Faust and Smart Keyboard, which is a Faust library that allows to build smart keys and sliders optimized for touchscreen devices. There are two keyboards with this frequency range. It's possible to control the low-pass filter cutoff frequency, and there is a dry-wet parameter. So if the parameter is completely dry, then only the carrier signal is audible, and the app becomes basically a synth. Whereas if the parameter is completely wet, then only the processed carrier is audible. It's possible to control the carrier gain by sliding up and down on the keys, and this provides a general volume for the app. Also, there is a control over the modulator gain, which sets the sensitivity of the vocoder. So basically, how loud the voice has to be to trigger the vocoder. The carrier is made of a blend of a square wave and a sawtooth wave, and it's possible to control this to change the timbre. Also, if the phone is shaken, then this triggers a vibrato effect. There were some hard-coded parameters, specifically the bandpass filter's number and Q factor, the low-pass filter type and its cutoff frequency range, and the envelope follower's attack and release times. So this is the application interface. The app is intended to be played with the Android keys facing the body, as this is where the smartphone microphone is. So this way it kind of resembles a flute. The two keyboards lay on the two sides of the screen, so it's possible to play with two hands simultaneously. And on the center, there are the controls previously mentioned. All of these are sliders. So this is the low-pass filter cutoff frequency, the wet and dry parameter, the voice gain, modulator gain, and the blend between the square wave and the sawtooth wave. Sliding up and down on these keys controls the carrier gain, so the overall app volume. So during the development of the application, several issues were encountered, which are directly linked to the disadvantages of using a smartphone as a musical instrument, explained before. In particular, the level of polyphony is limited by the computational power of the smartphone. And since there are many different kind of smartphones out there with different computational capabilities, it's not easy to set a level of polyphony which will work for each of them. Also, playing while holding the smartphone is not very comfortable because one hand is busy holding the smartphone and it's difficult to do that while playing. Also, most smartphones present the speaker next to the microphone, and to avoid feedback issues, it's necessary to use either a microphone or an external speaker. But this makes the instrument not compliant with Geiger's principles. For overcoming the last two issues, a case prototype was developed, which is intended to hold the smartphone, making it easier to play and provide amplification. Since this work is at the stage of proof of concept, only a cardboard version was created. So this handle is intended to hold the smartphone while leaving the hand free to play. And a tiny rail placed here would adjust the height of the handle to adapt it to different hand sizes. Then this part here is intended to include an external speaker. Now, when the actual case will be built, it will be necessary to address the problem of amplification. In fact, there are two main ways of including an external speaker into the case. One is to directly include the speaker into the case, and this is the more practical solution since this would make a coherent design. But of course, this is also more expensive. The other solution would be to develop a universal speaker holder, but of course, it would be difficult to deal with different speaker sizes. So this is an issue that needs to be addressed in the future. Now, a short video will show the working application.
Okay, so this is the instrument, and well, as you can see, this is the cardboard prototype of the case, and unfortunately the Bluetooth connection doesn't work in this speaker, so I have to use a jack cable, but ideally this would work with the Bluetooth, so there would be no cables hanging around. Now, first I'm gonna put the app on dry mode, so full dry, so so I can show you the timbre, the timbre controls. So this is the sound, and it's possible to control the low pass filter cutoff frequency with this slider, and this tone control controls the blend between the square wave and the sawtooth wave. So these are the synth functionalities, and now if I put the app halfway between wet and dry, I can start speaking into the microphone, so the vocoder is triggered. Now there is this voice gain control, and if you can see that now the vocoder is way louder, and if I put the wet, the app on full wet, then the synth doesn't work, and it only works with the vocoder. Okay, so this was a quick tour of the app. I hope you enjoyed it.
So I would like to thank you all for your attention, and if there are any questions, I will be happy to answer.
Okay, so that was it. Thank you for all the presenters. And now it's time for questions. All right, so we had some questions here. So Igor asked something from the first speakers. Did you estimate some performance measure how well the physical model works? For example, comparing the spectrum values between real and model tones. But now the authors already answered that unfortunately they had no access to real tones since the instrument cannot be used anymore. It's in the museum and so on. What else? I didn't have sounds from the original violin harpa, but we did try to compare the sounds produced with the recordings of other violin sounds. We did compare spectrograms, but more subjective than using an objective comparison measure. For instance, we checked whether we get similar overtones. Okay, and then regarding the sounds, main focus was put on checking the friction interaction between the bow and the string, particularly the presence of stick slip motion or Helmholtz motion, which tends to cause triangular waveforms. All right, so that was the first question to the first paper. So, okay, that's quite unfortunate, of course, that the instrument is there and you can't in the museum you can't play it. Can I ask the authors? Could you at least go and knock it, like for example, from music, like these wooden musical instruments? The body, the sound box is quite important for the sound quality. One idea is that you actually take, for example, like a pencil and drop it on the bridge, and you get this gentle boom, like a knocking sound, and actually from that you could already measure things like body modes, for example. Have you considered something like that?
It's a good idea. We didn't think about it at the time, but yeah, we could just kind of take the impulse response of the body itself and then try to model the instrument in a different way, where we just bow the string alone without connecting it to this plate and apply this impulse response on top of it, like convolve this impulse response. Yeah, it's another way to go, and we didn't think about it at the time. I think the idea was that we wanted to see if we can model this plate in these kind of rectangular coordinates and then kind of sculpt this shape around it. And it was more of an exercise of, let's see if we can do this as modeling plates connected rigidly to this string. But of course, this rigid connection is also not completely correct. I mean, the bridge in a violin is not perfectly rigid. So we would, if it wasn't a super accurate model of the violin, but it was something that produced hopefully similar sounds and that could be used in this application that I feel was focused more on the VR and the AR experience of the museum goer.
Right.
Yeah.
Very good. Thanks. And Stefania and Serafin also comments in the chat that you can't touch the instrument. It's in the glass cabinet. Well, you could give the pencil to the museum personnel and ask them to gently drop it. It doesn't break anything, but you have to have your microphone there and measure. Then anyway,
then it's like in the cartoons, and the violin will just completely break apart.
Yes.
No,
I hope not.
There's a real kind of politics of handling these heritage objects, because I'm also working with heritage objects that are in glass cases, and I'm expected to kind of work on emulations of them, and it's really a process. It's sometimes a very long discussion with museum staff about how that can be done. And luckily, I've not the Datatone. Luckily, is not a museum object, but there was another one that I was actually allowed to take out of the case and completely dissect, which was really fun actually. But it's having the let's say the guidance or the badge of an expert in a field or something, one that the museum recognizes as an expert in the field, helps a lot.
Okay, good. Thanks for the comment, Derek. And now in Oslo, we have somebody's yellow hand.
Yeah, that's me again. I have a question to all of you, actually, and it's as you know, I'm interested in instruments and also how you use instruments and the embodied aspects. And I think all of you have been, I guess, focusing more on the sound side here, which makes sense. And I think you've done fantastic work. So this is not meant as a critique, but perhaps more as a reflection for all of you on how to interact with these things from a more kind of embodied perspective, because working with kind of screens or mice and keyboards and these things, it's a bit different type of representation and interaction as well with these objects that you're trying to model. And I guess you've already thought about this in your various design processes, but also how to move this forwards. Is that something you could reflect on? Any of you?
Who wants to go first?
I can jump on that one just because it was something that that was a really valuable learning experience for the students that did the emulation. In my case, was that it wasn't reducible to this thing on the screen, that there were these really physical parts, not only of having kind of tactile feedback from the knobs, but even the way that this particular synthesizer is patched is very physical. It's very tactile. You're kind of locking these Lego blocks together, and it functions in a very different way than kind of drawing these PD patch cables. So they definitely learned a lot about the lack of tactility, let's say, from doing a screen-based emulation.
Yeah, regarding the violin, I actually extended the model and implemented it in a real-time application further along in my master thesis. And there we actually control the sound by using a sensor morph, which is basically a touchpad with pressure sensitivity. So there we kind of had a bit more degrees of freedom with respect to the interaction with the sound. So we actually kind of, in my thesis, I modeled the bowing interaction by the pressure with which you apply on the touchpad. And you could also change the position of the bowing by moving your finger around the touchpad. So I think the more degrees of freedom you have in your interaction device, the more creative you can get, I guess. So yeah, but with respect to the Amoeba Violin and the museum project, it was more reproducing the sound samples that were generated beforehand.
As in my case, the idea was that the vocoder usually comes in the form of a huge keyboard or maybe soft synths. So usually what the user does is to interact with the computer or usually a huge device. And the idea was to create a compact version. So it's portable, but also the sound source is closer to the body. And it's easier to interact with the instrument too, also with the body movements. So maybe also, I don't know, changing the position of the speaker with respect to the audience can change the way the sound is perceived. So it was kind of a tentative to create a more a more compact version of this effect, which is usually more it has a different form. This was the idea.
All right, thanks. So everybody all authors had something to answer to Alexander. Alexander, is that your yellow hand still showing, or is it another hand?
Yeah, I mean, I have a question.
Yeah, they look so similar, those hands. Go ahead.
Still the same. Now, actually, I have two questions. One for Ricardo, one for Derek. I'll start with Ricardo. The first one is if you measured, or if you have any idea about what is the latency, sound in to sound out, and the latency between touch and sound output. And for Derek, question is a little bit more complicated. I mean, I think that it's not easy, but it's feasible to reproduce an interface for the name, data system 3000, or because one of the limitations, one of the feedback that you get, the lack of a physical interface, and we can easily build one, but I think it's much more difficult to achieve a much higher fidelity of the sound of the instrument. I believe that you re-implemented digitally the same sound synthesis model, but I believe that if you want to go very close to the original sound, that is also part of what you want to experience. You really need to model the circuit, and I believe that in this context, we don't have the resources for doing so. So I believe what could be a feasible alternative to achieve a better fidelity in terms of like, how does it sound? How similar it sounds? I don't know if you express, if the question is clear.
Okay, so I can start. I didn't measure the latency. I run actual measures. But of course, it depends a lot on the device and the kind of phone that is running the application. I tried on a couple of Android devices, and the latency wasn't perceivable. So it was very smooth in the way it worked. It was possible to play different melodies without hearing any delay. But of course, I had to. There was a trade-off in the implementation of the application. There was a trade-off between the level of polyphony that was allowed and the computational power requested, because of course a higher level of polyphony requires more computational power. And since Android devices are where there are a huge variety of devices with different computational powers, it's not easy to set a standard, for the level of polyphony which can work for each device in the market. So that's something that would be worth to investigate, to maybe add a control to set a different level of polyphony depending on the computational power of the smartphone, or something, or maybe try to find something that works for every device. That's something worth investigating.
Before I jump into the question, actually, Ricardo, I have a really related question, because I was also interested in the latency, and it's something that you notice in the demo very quickly, is that the sound of the voice comes out quite a bit later, and that's there's, when you think about latency, there's the latency of the interface itself, like whether I hit it and it goes bang right away, or it takes a little while. But also when you're dealing with the voice, that's something that we're so tuned into kind of mentally, about like lags and latencies in vocal sounds, because we spend so much time paying attention to them. So any sort of latency in the input and the output there, I think perceptually becomes even more apparent than in the kind of, when I hit it, does it go bang? So I guess it's not a question, it's just an observation.
Sure, that's absolutely right. And of course, it's more perceivable with the voice. For sure, it's necessary to run some measures on the latency, and probably also to tune the internal parameters to adjust latency. That's but of course that would be something. Well, it would be necessary to work on different devices to try something that can work for each of them.
Yeah, and that could be something that you could address a bit in an evaluation with users, as well as how noticeable or annoying that latency is, because of course, if they're running it on different platforms, it's going to be different on each one of them. So
yes, totally.
Great. Yeah. Okay, Stefano, thank you for a deep question, because it covers a lot of stuff, and I think that your question fundamentally gets to issues of intention. What is the intention of the project? In my case, well, I'll go back for a second, and I'll say yes, absolutely. If what we wanted to do was to collect impulse responses from the filter banks in the Datatone, for example, or if we wanted to make representative samples of the different waveforms of the oscillators, there's a lot of techniques for getting really close to that. I've been looking a lot, for example, at the stuff that's been going on over in your lab, Vesa, with using different sorts of machine learning stuff to emulate I believe it's the guitar pedal circuits, isn't it, that somebody's working on over in Helsinki? Is that right? Or was that going on someplace else? Okay.
We are doing something like that, of course.
Yeah.
Yes.
Okay. Yeah. So there's that approach of do you want fidelity to the impulse responses of a filter? Do you want fidelity to the waveforms that are produced by a specific kind of analog electronic transistor based oscillator or something like that? And definitely there's lots of work being done. In the paper, I mentioned a lot of the Arturia, the commercial VSTIs that are based on old analog synthesizers like the Synthi AKS and the Buchla and the different ones like that, the ARP 2600. and they've done like incredible amount of work modeling waveforms and things like that. The focus of what we could do also with a group of students in just a couple of weeks wasn't that extensive, of course. But the other thing is that I think that the focus of the research that I'm interested in doing isn't in making kind of a one-to-one copy. I really enjoyed the part of Ludwig's keynote this morning, where he says that every sort of a model is a necessary reduction of a system from the system that it's trying to emulate. And I think that the thing that we're interested in the most are the affordances and the kind of the ethics of these instruments. Why were they created? What sort of systems in a kind of an institutional sense were they meant to address? The Datatone is a really interesting one for that, because it was actually meant as a pedagogical instrument. There was supposed to be one in every Swedish school for every Swedish music class to learn about synthesis. And the way that the user of these instruments kind of physically interacts with them. So this question about the physical interaction is also really important. So this particular work emulating the Datatone this time was largely about kind of pulling students into the project and seeing how they would approach that problem. And they approached it kind of, you know, flattening out a lot of things. You flatten out the sound a bit by just kind of using the default filters and oscillators that are available in pure data. And you certainly flatten out the user interface by not having this kind of physicality. And both of those things can be built on for sure with let's say, more time and more resources.
Thank you, Derek. So we are running out of time, so I don't see any more questions, but I might like to ask maybe one more question from the authors of the first paper. So if Krisa, are you the first author? You are. Can't hear you at the moment, however.
Is it better now?
Yes, now it's much better because we hear you. Yes. So how can you briefly explain how did you divide the project? You were, I think, quite many people doing the virtual instrument project and related applications. Please.
Sorry, could you repeat? Sorry, I didn't hear you.
So how did you divide the work in the project? So there were quite many tasks.
Sure. So obviously Marius did the work around sound. I worked on the visual part. I created the instrument. I have some background in 3D modeling and stuff like that. And Sophia and Panayota worked on the programming. They created the application and everything that needed sorry, they created the application and they did most of the UI stuff, and I helped a little bit with that. But yeah, that was it. It was quite a few people. And Stefania was our supervisor. She took care of all of that.
Very good, thanks. Yeah, you had quite a team, but there was a lot of subtasks.
Quite a few people. Yeah.
Yes. Good. Thank you. I think now it's almost 10 past. I think we should wrap up here. And thanks everybody. Thanks for your presentations and for coming here to the Q&A session. So it's over to Prithvi then, right?